So thank you very much for the invitation. It's a great pleasure to be here. Some more people will arrive soon. So I'm from the ELTE, from the Faculty of Informatics. And I will explain some work, which is joint work with Torsten Artenkir from Nottingham, Jorgo Shamun from École Polytechnique in Paris, and Michael Schulman from San Diego. And it will be quite high level, so I hope that everyone will understand everything, even if it's I'm coming from slightly different tradition. You can maybe you should do on the other side there. That's yeah. Does the sharing work and everything? Okay, good. Okay. Yeah, so I start with Paul Benacerraf, who was a French-born American philosopher and wrote this paper, What Numbers Could Not Be, and was complaining about the set theoretic foundations having the issue that there are different representations of the natural numbers, and they are not really the true natural numbers, but they have additional properties. So, for example, if in set theory you prove something about the Zermelo natural numbers, then it's a priori not clear whether your proof also holds for all the other representations of the natural numbers, like von Neumann's one. Sorry, does this work? Yeah, okay. Yeah. There are set theoretic propositions which distinguish the two, even if normal mathematicians never do anything which distinguishes these two ways of implementations. And there are lots of, and then he was proposing that there should be a structuralist language for mathematics. So this is like a philosophical structuralism, where you, and then there are lots of different names for this, the same idea. So where you use abstract definitions, or you reason more abstractly, or in computer science or programming, we call this representation independence or information hiding, which is also very important for computer programs, where you work with an abstract interface and only that's what you use, and then your code is more reliable because for every implementation which implements that abstract interface, it should work. It's also called uniformity or naturality in category theory, where category theory started from this idea of naturality and how do you form the how do you do reasoning at a higher level, which can then be applied to lots of different areas. And then another name for this is parametricity, which I will explain here, which is a way of formalizing this idea. So this was given by John Reynolds, an American computer scientist who's famous for lots of contributions. So he invented the polymorphic lambda calculus at the same time as Jean-Yves Girard, the French logician. So Girard called it System F, Reynolds called it polymorphic lambda calculus. There are some very important computer science contributions like definitional interpreters, defunctionalization, which is for compilation of functional programs, separation logic, which is now a very big topic for reasoning about operating systems. This is the kind of logic that people use in practice. And there's also parametricity, which he introduced in this paper, Types, Abstraction, and Parametric Polymorphism. And it's a very nice paper. I recommend everyone to read it. And I couldn't resist, and I have to read the parts of it. So it starts with a fable, in Hungarian fabula, or in Latin. So which is a different way of saying, stating the problem that I said for natural numbers. But now, once upon a time, there was a university with a peculiar tenure policy. All faculty were tenured and could only be dismissed for moral turpitude. So what was peculiar was the definition of moral turpitude, making a false statement in class. Needless to say, the university did not teach computer science. I mean, all the faculty would have been fired. However, it had a renowned department of mathematics. And one semester, there was such a large enrollment in complex variables that 2 sections were scheduled. In one section, Professor Descartes announced that a complex number was an ordered pair of reals and that 2 complex numbers were equal when their corresponding components were equal. He went on to explain how to convert reals into complex numbers, what I was, how to add, multiply, and conjugate complex numbers, and how to find their magnitude. In the other section, Professor Bessel announced at the first class that the complex number was an ordered pair of reals, such that the first of which was non-negative, and that 2 complex numbers were equal if their first components were equal, and either the first components were 0 or the second components differed by a multitude of 2 pi. He then told an entirely different story about converting reals, addition, multiplication, and so on. Then, after their first classes, an unfortunate mistake in the registrar office caused the 2 sections to be interchanged. Despite this, neither Descartes nor Bessel ever committed no moral turpitude, even though each was judged by the other one's definitions. So that's remarkable, no? So the reason was that they both had an intuitive understanding of type. So having defined complex numbers and primitive operations upon them, thereafter they spoke at a level of abstraction that encompassed both of their definitions. So, and the moral of this the fable is that the type structure is a syntactic discipline for enforcing levels of abstraction. So this was a proposition for using types or typed calculi, typed languages, typed logics for a structuralist foundation of mathematics, or a structuralist way of writing computer programs. So I just read the second part here. So although both lecturers introduced a set of instar of sequences of integers and spoke of sets such as instar plus complex, so there's the disjoint union of instar and complex, or instar Descartes product complex, and instar arrow complex, so function space from instar to complex, they never mentioned instar union complex or the instar intersection complex. Intuitively, they thought of sequences of integers and complex numbers as entities so immiscible that the union and intersection of instar and complex are not even defined, right? And that's this kind of intuition that's also for natural numbers. The kind of propositions which distinguish those are some kind of evil propositions. We don't want to say that. And the same here, these instar union complex and instar intersection complex are evil things. So we are not allowed to say that. So, and Reynolds formalized this idea of, or made precise this idea of representation independence in the context of the polymorphic lambda calculus by saying that everything preserves relations. So I show you what this means through some examples. And later we will see it a bit more formally. So let's see, this F is a term. It's on the left-hand side of the column, and this gives its type. So this is a polymorphic function. It's a function which for every type goes from an element of A into an element of A. And in a language where you have this representation independence, you know that this is kind of a definition where it only is allowed to use the interface. So the interface is that there's a type and that type has an element. And I don't know anything more about this type. Like I don't have access to its internal structure. I really don't know anything more about it. And then I need to return an element of A. So the question is, what can this A be? Can I say something about this F, how this F behaves? So there's a very easy way to define this F, just the identity function, right? So it takes a type A as an input, then an element of that type A, and then it could just return that element, and that's well typed, that's a good definition, and that's allowed, but are there more elements of this function or not? So that's the question. And this is the statement that this F preserves relations. So R is a relation. So this is how we, okay, maybe one more syntactic thing is that the arrow function space is right associative. So this is called a curried function. So the input is a pair of a type and an element of it. So the input, you can think about types as sets if you haven't encountered type theory before. So you can think about it. A is a set, but it's some kind of set with some abstraction enforcements. Okay, so the input is a pointed set, say, and the output is an element of the input set, right? Okay, and this is how we write a binary relation on types A and B, or on sets A and B. It's this characteristic function style representation that this type here, you can think about it as a Boolean or a proposition. So for any type A and B, I know whether that pair is in the relation or related. And then we have a witness small r that small a is related to small b, and that F preserves relation. It means that for any relation and any two related elements, if I apply that function to the small a and big A and small a and big B and small b, then they will be related. So functions preserve relations. That's you see, if there's a relation for the input, if the inputs are related, then the outputs are related. And now if we choose some more specific relations here, so let's take the R relation to be a graph of the function G, okay? And then we have an element A. Then in this case, parametricity, which I call this FP, so FP is the parametricity of F, and it needs as parameters, as inputs R, big R and small r. It says that basically this function G commutes with F. This is like a naturality property. In fact, it says that F is a natural transformation. That for any, if you apply the G first to some input and then you apply the F at the type B, it's the same as applying the F first and then applying the G. So let's be even more specific and choose G to be the constant small b function, okay? So I have some small b, an element of B, and I choose G to be this function, then parametricity of F says that because here, right, this is the input of G, and because it's the constant small b, then it discards the input and just returns B. So I get that B is equal to F applied to B, right? So this means that this F is indeed the identity function. There's no other elements of this type, okay? So you cannot write any other F here. So for a slightly more interesting example, so here's another F, which also is a polymorphic one. So polymorphic means it works for every type, and it's now list of A to list of A, or sequences of A to sequences of A. And for this parametricity says that if you have a relation A and the sequence of A's and the sequence of B such that these sequences are pointwise related, then the output sequences will also be pointwise related. So here there should be a star. I forgot the star here because the outputs are sequences. And again, we can specialize or take this R relation to be just graphs of a function. Why don't you see them here? So now I'm explaining what does Reynolds parametricity say for elements of this type, which is polymorphic functions, which work for any type A or any set A, and map sequences of A to sequences of A. And it says that these also preserve the relation. So if I choose the relation to be, again, a graph of a function, the function G, so RAB is just a graph of the function. This is how it's defined. Then I get that R star, which is the pointwise application of R on every element of AS and BS, says that if I pointwise apply G to AS, then I get BS. Then I get the following theorem about F. Even without knowing anything about F or seeing the definition of F, I know that it satisfies this theorem by Reynolds parametricity. is that if I first apply G point Y to the list, and then I apply F at B, is the same as first applying F to the list A's and then applying G point Y. So let's be even more concrete. So like F could be the reverse function, which reverses a sequence. Okay, that's polymorphic, it works for any type. And G could be some code function, computer science example, where we code a character with ASCII code or something like that to a natural number. So it doesn't matter if you have a list of characters and you first point-wise take all the characters and code them and get their ASCII code, and then I reverse the string, or I first reverse the string and then take the ASCII code. Right? Or another example is F is the tail function, which omits the first element of the list, and G is increasing every number by 1. It doesn't matter if I first increase the numbers, then forget the first one, or first forget the first one and then increase the numbers. And here is a non-example. So what if F is the function, the odds function, sorry, the type is wrong because this should be list of n to list of n. So odds function from list of n to list of n, which takes out the odd numbers and leaves out the even numbers and leaves only the odd numbers in the end. And G is increasing. So for this, it's not the case. And here is a counter example. Like if I take the odds numbers on 1, 2, 3, then it will be just 1, 3. If I increase them, I get a list of lengths 2. If I go the other way, I first increase them, then I get 2, 3, 4, and the only odd number is 3, so it's a completely different list. So why it doesn't work here? A question to the audience. Okay, maybe the question is too obvious, that's why people wouldn't answer, right? Because this has the wrong type, right? It's not polymorphic. Odds only works for natural numbers or some kind of numbers where there's a you can meaningfully say whether a number is even or odd, but this theorem only applies to polymorphic functions, which work for any type. Okay, so now here are again questions for the audience. So now you have some intuition for what this means, that what this parametricity means. So this F, there was only one such F. So now there are questions A, B, and C. How many Fs are of this type? So here, if I think about this as an abstract interface, I get input is a type A and an element of A and another element of A, and I can return an A. So what can I do? Right? I can only return one of those two. So there should be 2 elements of this. How many elements are of this one? Here, the abstract interface is that there's a type, or there's a set, and I need to return some element of that input set. But I don't know anything more about the input set. That I only know that it's a set or it's a type, right? Yeah. So there's no elements of that. Okay. And what about the last one? So here I have the abstract interface is there's a type, then it has an element, and there's an endo function on that type. These are the inputs, and I need to return an element of A. So how many such Fs are there? Okay, now I wait. And you can, okay. Because you've seen this before. Yeah. Okay, right, so that's correct. There are infinitely many, because what the only things I can do is either return that A or apply the endo function to it a finite number of times. And then there's exactly as many as integers. So so the previous examples of this representation independence can be described by category theory, saying that every F function, such polymorphic function, is a natural transformation. So, for example, the first one where I just go from A to A, it's a natural transformation between the identity functors. But this doesn't work for higher order types. So that natural category theory is not good enough to make me prove this one, that this is omega, because this is a higher order function. So here I cannot say what functor is this, because this is not a functor. It's some kind of pro-functor where they are both contravariant and covariant arguments, and it's something much more complicated. I mean, there is work towards this to describe this. It's called directed type theory. But the first 2 examples are covered by this. Now you can say that representation independence is preservation of not homomorphisms but relations, and that's parametricity. So this is a nice theory. Okay, I haven't said this, but I want to add this parametricity to the foundations of mathematics. So as a type, if you use type theory as a foundations of mathematics, then it is parametric. But if you add parametricity, it becomes inconsistent with the law of excluded middle. Or you can say that there's preservation of isomorphisms in general. And if you're an isomorphism, that the variance problem disappears, because you can always go both ways. So there's no variance issue. And this is what people work on in homotopy type theory. And there's Vovotsky's univalence axiom says that everything preserves isomorphisms, is exactly in the same way as Reynolds says that everything preserves relations, and that is consistent with the law of excluded middle. So it's you don't have to choose that you are classical or constructive there, because both it has models in both worlds. Okay, and I wanted to show another example. I mean, this example, which cannot be derived from naturality. So here, this is for this type, which should have infinitely many elements. I want to prove that this has infinitely many elements. Okay, so exactly natural number, many elements. So in fact, what I really want to prove is that this type is just the type of natural numbers. Okay, or like you could say that this is exactly or it's isomorphic to the type of natural numbers. So what does Reynolds say here? It says that if I have a relation between some A0, A1, then I have some Z0, Z1, which are Z0 is in A0, Z1 is in A1, and they are related by this relation. I call it ZR, okay? I call it Z because that's like 0 for natural numbers. Then I have S0 and S1, which are like successor for the A0 and A1 types or sets. And I have that, this S0 and S1 preserves the relation. So for related A0, A1, S0 of A0 is related to S1, A1, okay? And then I have that any such F respects the relation, so which means that if I apply F to this R and ZR and SR, so I apply it to related elements, then the outputs will be related. So F of the applied to A0, Z0, S0 will be related to F applied to A1, Z1, S1. What I want to prove is that this type is the natural number. So how do I say that it is natural numbers? The easiest way to say it is that natural numbers is the initial pointed set with an end function. Okay, so a natural number algebra is just a set which has an element and there's an end function. So there's a set, a 0 and a successor operator, and it's the initial. So I call it PSE. It's initial. That means that there's a unique homomorphism, unique PSE homomorphism into any other PSE algebra. And in fact, it's very easy to show for this type that there is a homomorphism into any other PSE algebra, because here I define the natural numbers as a PSE algebra, so not will be just this. It's very easy to define 0, and it's very easy to define successor with this. This is also called Church encoding of natural numbers. So this technique was invented by Alonzo Church in the 30s or 40s. And I call it iterator or recursor, or ita is the unique morphism from not 0 SOC to AZS. So from the not 0 SOC PSE to AZS PSE. And this is already weakly initial because there's a homomorphism. Ita is a homomorphism, which is witnessed by these two equations, which are just true by definition. And now what we need is that it is unique. So for any other PSE homomorphism G, which goes from not 0 sub to AZS, we have that G is equal to the iterator, to this eta AZS. And here parametricity comes for help. So using parametricity, I can prove that this diagram commutes. So this is these are the objects are algebras, PSE algebras, and the morphisms are all homomorphisms. So what if I have two PSE algebras and the homomorphism between them. Then I can take the iterator from the proposed initial algebra to the A0 algebra or to the A1 algebra, and I can go A0 and then G, and it should be the same. So this is a direct consequence of parametricity, where we just say that, again, as before, we take R to be the graph of G. And here we also use that, we need to use, that G is a PSE homomorphism that we assume. Okay, and in particular, if you use this for this diagram, now we use the previous theorem for this diagram, where we instantiate G to be eta, and this is an arbitrary algebra, then here is the statement that we get, and if I just, by definition, this statement says that if I have an n, a natural number, in this algebra, an element of naught, if I apply it to naught, 0, and so on, then I get the same thing, okay? And using this, we can reach our goal for any arbitrary G. So if there's a G here, then I can go first an eta naught 0 sock and then G, or directly iterate into A. And by our previous lemma, we had that these two are equal. And by the second lemma, I get that this here, the n naught 0 sock, is just n. So I'm done. So I proved that this is natural number. So I could prove that the Church-encoded natural numbers are indeed the natural numbers. So they have an induction principle. Induction for natural numbers is equivalent to this uniqueness property. Yeah. So okay, and now I will be very quick. So all of this, what I showed previously, is examples of parametricity for the polymorphic lambda calculus, which is a programming language. It's a total programming language, but you cannot encode all of mathematics in it. But in type theory, you can encode all of mathematics. And this parametricity theorem was extended from polymorphic lambda calculus to Martin-Löw's type theory in 2012. And type theory is a language for the formalization of mathematics, and there are lots of computer proof assistants which were used to formalize lots of mathematics, especially in Lean. There's the project by Kevin Buzzard where they basically formalized all of undergraduate mathematics, and lots of really cool stuff like results of Peter Scholzer were formalized in this, and now Terence Tao is also learned Lean himself to encode his theorems in Lean, and it is structural. Now we can call it structural because it satisfies parametricity. And the nice thing about type theory is that parametricity theorem of type theory can be expressed in the same language. So when we say parametricity of the polymorphic lambda calculus, we need to go outside of that language. So it's a meta theorem. But in type theory, it's like it can express its own parametricity, but it is still a meta theorem here. And now the contribution of the things that I want to say is how to internalize this theorem. So that's a language of mathematics, which is a structuralist language, and it even knows from itself that it is structuralist. So there's internally all the theorems that I showed before, that an element of the type it's the identity function that can be actually proven internally, but it is quite difficult to do this, because if you want this, then you add the weakness of parametricity in the language, but that also needs to be parametric, and that results in some higher dimensional spaces. So in particular cubes. So this is what the spaces look like for external parametricity. So this is a type, and this is the parametricity relation for that type, so the span of that type, because this is a set together with two elements, so that's equivalent to a relation, and then you can iterate this parametricity and you get lots of higher relations. And here you have the cubes, here you have squares, here you have 3-dimensional cubes, 4-dimensional cubes, and so on. And if you make it internal, then you need these degeneracies. So you want to go from lower dimensions to higher dimensions, and then there are ways to swap these dimensions. And This is a very complicated syntax. It becomes a very complicated language if you want to make all of this precise. And there were ideas on how to do this in a nicer way, but they result in some substructural theories in which substitution behaves strangely, which we don't like. So our contribution is that we made this all nice. So it's a small extension of type theory where you add these parametricity operations. So in fact, you only need to add these new operations and 5 equations, and it becomes a nice, simple structural syntax, and everything computes. So it's a programming language. So we proved that it has canonicity. Okay, that's it. And sorry for taking longer.